So, okay, so yeah, I'm going to be talking about how to get fake data instead of how to analyze real data. So what I work on myself is the warm hot intergalactic medium, basically the WIM. So that's basically this sort of 10 to the 5.5 to 10 to the 7 Kelvin gas in the IGM and CGM. So circumgalactic medium, that's gas around L-star galaxies, and they call it intergroup medium or intercluster medium as you go to higher masses, basically. But what I do is I look at, well, line absorption, working on line emission of it now a bit, but this talk is on line absorption and sort of how to get these mock absorption spectra from cosmological simulations. So that's useful for making predictions for observations, for comparing to the very scarce observations we have of these things with current instruments, and also just useful for things like testing pipelines for these observations with upcoming instruments. So I work with Joop Shea at Leiden, and my email address is on here as well. So yeah, I'm going to start with just basically a bit of an introduction to cosmological simulations. So don't panic. So this is this slide is mainly for you guys to look up afterwards and look at all the links. But basically, if we have like a general set of cosmological hydrodynamical simulations, there are review papers available for these things, and there are a lot of different simulations out there. I'm going to be talking about Eagle because that's the thing I work with, so that's the one I know, basically. So cosmological simulations in this context basically means that you just take a box, a certain volume in the universe, and you simulate that. So you don't focus on necessarily one cluster or one galaxy, which assumes simulations. That's a different category of things there are. But you're just sort of looking at a volume-limited sample of objects. These boxes are also periodic, just to deal with, you know, not having weird boundary conditions. Eagle is a smooth particle hydrodynamic simulation, which means that gas is not tracked in sort of volumes in the simulation, where you track how gas moves between these volume cells. Instead, the gas is divided up into these mass resolution elements, which then move around, and you know, we have more particles in denser regions, which means that the resolution in Eagle is fundamentally a mass resolution given here. This is quite common in cosmological simulations because it sort of naturally allows you to focus your resolution in galaxies. So I had a movie that's not going to work in the PDF, but you can sort of roughly see the sort of filamentary cosmic web in the temperature and the metallicity, which are, you know, two of the variables traced in Eagle. Luckily, I have a backup here, which just shows sort of that we trace the total mass, which is mostly dark matter over time, redshifts 4 to 1 to 0, as well as the gas, which has hydrodynamics affecting it, the temperature, the metallicity, and the stars. So we have stars forming in Eagle because these simulations, they can be used for the WIM, but they're actually mostly focused on galaxy formation. So you want to form stars, you get metal enrichment from these stars, which is also what allows you to predict metal absorption lines from the simulations. So yeah, roughly an overview of the physics traced in these things. So you have obviously gravity and hydrodynamics. So you have gas, and you have this. You need to have this sort of first order, certainly, and also just generally gravitational collapse. In order to actually get galaxies, you need to let this gas cool in the center of halos. So you also have radiative cooling for the gas. In Eagle, this depends on the abundances of the different elements, which are individually traced. You have star formation because you want to form stars, but you also need stellar feedback. Otherwise, what happens basically is gas cools into the center of the galaxy, it forms stars, and it just keeps forming stars. And you know, if you look at the galaxy stellar mass distribution, they end up way too massive. So what you do is basically you also need to model supernovae going off. And for the enrichment, they also in Eagle have AGB winds and type 1A supernovae. So this works up to roughly Milky Way mass galaxies. If you get to more massive galaxies, the stellar feedback, the supernovae don't actually quench the star formation sufficiently, so you also need AGN feedback. So you need AGN kicking or heating gas around. In order to do that, you need to put black holes in. That's typically just putting a black hole in any halo that's sufficiently massive and doesn't have one, because we're not entirely sure where these things come from in the very early universe. But that then, these feedback mechanisms, then they're calibrated basically. So the way these are done, there are some free parameters in there that are not necessarily known from sort of first principles. These are calibrated to get, in Eagle, the redshift 0.1 galaxy stellar mass function, black hole mass, stellar mass relation, and roughly the galaxy size is correct. Other simulations will have sometimes calibrate to different things, or a few more things. That's for Eagle. And and other simulations, so not Eagle, but other simulations might also include things like magnetic fields, thermal conduction, dust. There's all sorts of physical processes you can put into these things. So some things to look out for if you're doing sort of this analysis of these simulations are, first of all, because the mass resolution is only 10 to the 6 solar masses roughly, can't actually model this multi-phase ISM. And in order to make this, to sort of get this to work correctly, you basically need to put in a pressure floor here. So you keep the gene scale resolved in the ISM. That pressure floor does mean that if you look at the density and temperature of gas that you get directly from the Eagle simulations, that the temperature is not actually going to reflect a reasonable temperature for the interstellar medium. So sort of the standard practice in Eagle post-processing is that if gas is star forming, you calculate the ion balances, assuming that the gas is at 10 to the 4 Kelvin. Another thing to look out for in these simulations is, like I said, this feedback that's calibrated. So the issue with this feedback is basically if you don't have single stars, so you have a group of stars of one age that is roughly 10 to the 6 solar masses, sort of a star particle is what that's called in Eagle. And if you just, you take your initial mass function at each time step, you calculate how many supernovae should be going off, and you just put that, put the energy from that in Eagle, that's a thermal energy, into 1 10 to the 6 solar mass gas particle. What happens is the temperature barely goes up. It stays very close to that peak of the cooling curve at 10 to the 4 Kelvin. The energy is basically immediately lost at radiative cooling, and it doesn't actually quench anything. So this problem also exists in simulations where instead of heating particles, they kick them with a certain velocity. That also just doesn't do very much to these sort of massive resolution elements. So there are different ways that different simulations handle these things. In Eagle, the strategy is instead of injecting energy at each time step, you save up the energy based on and you, at each time step, have a certain probability of heating a gas particle. So that gas particle, instead of then being heated by the thermal energy for one supernova, is heated by, to a fixed temperature of 10 to the 7.5 Kelvin for stellar feedback, 10 to the 8.5 for AGN feedback. So that puts it over the peak of the cooling curve. That makes sure that it can actually, do some work before it cools. And the probability of heating a particle is then set so that the energy injected, at least in a statistical sense, corresponds to what you'd expect to get from those supernovae. What that does mean is that you occasionally, especially close to a galaxy, get gas that is exactly at 10 to the 7.5 or 10 to the 8.5 Kelvin, which isn't necessarily a temperature you'd actually expect for a supernova bubble, for example. It's possible, but that's very directly probing a feedback parameter that's calibrated to get some global galaxy statistics right, rather than to like be in itself what you expect to see. So yeah, basically two big things to look out for if you're sort of post-processing this Eagle data is the interstellar medium has a like very simple model, and depending on what you're looking at, you might be quite directly seeing the parameters of a feedback model, and you need to be aware that that might not be entirely reasonable. So we have these simulations. So how do we actually get these mock spectra out of the simulations then? Well, inputs globally speaking, you have the simulation itself, the ionization tables, and of course you need atomic data. So from the simulations, you need some general characteristics of your volume. So you're looking at typically an output at 1 redshift, certain cosmological parameters, and a certain volume which you need to deal with the periodic boundary conditions correctly. So at this redshift, you also have a large number of gas particles. For those, you need to know, where they are and the peculiar velocity along the line of sight to correctly put them in redshift space. You need to know their size to know how distributed their ions are and whether they even intersect your line of sight. And the mass, temperature, density, and abundances, you need to actually calculate the ion content of each gas particle. So particle in this case is a volume element and not like an atom, or a resolution element. And the star formation rate, that's sort of a star formation rate larger than 0. You want to flag those gas particles because you want to set that temperature to 10 to the 4 Kelvin, sort of the standard practice. You can turn that on and off in SpecWizard. So ionization tables. So we're talking about very accurate atomic data here. This is the opposite approach in some sense. So we have these ion fractions from tables as a function of density, temperature, and redshift. So some assumptions going into this are sort of, okay, sort of the best you can do. So you assume ionization at equilibrium, optically thin gas, uniform but redshift dependent UV X-ray background. So this uniform background and a very old cloudy model. These two things are consistent with the Eagle cooling, because these cooling rates were calculated with this model. Those depend on your ion fractions. So you want to sort of calculate those ion fractions in a way that is self-consistent with your cooling model and the assumptions made within that simulation. So this is probably not, this is not the most up-to-date thing out there, but like there is a reason that I'm using this older model for these things. However, SpecWizard will accept any ionization table that just tabulates ion fractions as a function of these three things in the right HDF5 file format. Atomic data in SpecWizard, that's a wavelength and oscillator strength, so there's no transition probabilities because adding the Lorentz broadening is still on the to-do list. So right now it's just Gaussian lines, and they are right now just hard-coded into the SpecWizard code. Changing the values is relatively easy though. So for the code and documentation, this is on GitHub. There is a description in, for example, this one paper. There's a few others that have descriptions as well. I should say it's on GitHub. This is a code that's been passed through a few academic generations. I've used it for some specific things, and I know the documentation, how to use it for those, that's documented well. There are also options to use this, for example, for the OWL simulations that haven't been used in a while and might have been broken by more recent updates. So it's publicly available. It's not necessarily easy to get started using it. So if you have questions, you can just contact me. That's probably a good good starting point as well. So how it actually so then to get to the actual calculations, so first you have to actually select a sightline. Where do we want to calculate spectrum in Eagle? Then for each particle, you use these inputs, so the density, temperature, abundances, mass, with the ionization tables to calculate the actual number of ions in your element. Then the first step is that is then projected along your line of sight, just in position space. So you get sort of an ion density spectrum. And you also get ion weighted temperatures and peculiar velocities along your line of sight for each of these cells along your sight line. And then for each of those cells, you calculate an optical depth profile. So that's this Gaussian profile just from the position and Hubble flow and peculiar velocity. You center this, the normalization is based on the ion density and cell size and the atomic data, of course. And then the temperature sets the line width. So this is pure thermal broadening, although for a large gas particle, the sort of the Hubble flow broadening along the line of sight is accounted for in the previous step. So what this gets you is a so-called short spectrum. So it's a function of redshift or of line of sight velocity that gives you the optical depth for a single transition for a single ion. You can do this for a number of ions and a number of sight lines in one go. So just as an example, just sort of shamelessly plug my own work as well. This is an example of something you can do with these short spectra. So if you look at the top panel here, that's showing a 2 kilometers per second resolution spectrum from SpecWizard. This is for the oxygen 7 line, and then for oxygen 8, took the optical depth spectrum that was directly output, and then I also shifted and rescaled those optical depths to get this second doublet component here. And these are all some very rough mock observations that you can already make with this. So this is just assuming a flux effective area exposure time to get sort of roughly the photon noise, and a instrumental profile, which is just a Gaussian with the correct full width half maximum. This already gives you, pretty decent sense of what you could or couldn't do with something, at least as a rough idea. So another step you can do with SpecWizard is when, so you have these short spectra, so you have just these optical depths as a function of line of sight velocity for single ions at one redshift. So you can combine these things for a number of different redshifts, combine all the different ions and transitions that you want into one spectrum over a larger redshift range. So this is just an example of a long spectrum you can get. So this is up to redshift 1 using a sort of semi-reasonable set of X-ray ions.
Natasha, you're at 20 minutes, so you have 5 minutes left, counting questions.
Okay, so I will skip the next one. I'll just quickly go through this. So this is actually not something I've done analysis on so far. But if you want to, for example, test observing pipelines or, that sort of thing, then these long spectra are very interesting to give you sort of a reasonably realistic, given the fact that we don't have many observational constraints on these X-ray absorption lines, gives you a reasonable, realistic spectrum to input into your modeling. So I will skip the next slide and just go directly to the summary right now. So I've hopefully given you sort of an introduction into some of these cosmological simulations. There's a lot of information on temperatures, densities, abundances of element abundances in this gas, which you can use to make all sorts of interesting analysis of these the gas around galaxies in the intergalactic medium. If you're going to do some post-processing, though, it's just good to be aware of some of the model limits, like like the single-phase ISM and some possible artifacts, such as things that are fairly direct parameters of your feedback model. So the Eagle data, I should say, it's publicly available. There are public release papers and useful interfaces and all of that. So if you want to analyze Eagle in more detail, there are a lot of resources for that. And if you want to get mock spectra, SpecWizard does do that for Eagle. So this is available on GitHub. I have recently included also a rough installation guide for it. There isn't really a clear public release for this, though, because it's all a little bit, it's there, and you can ask me if you have questions. This is still in a bit rougher state in terms of like an actual public release. So yeah, that's kind of it. Any questions, I guess?
So thank you, that was really great. So I don't see any questions in the chat yet, so I'll give it a minute. You might, I guess you could go back to the slide you skipped for a minute, and we'll see if any questions come up.
I just saw one on Slack.
Oh, here's
can SpecWizard do emission lines? SpecWizard cannot do emission lines right now. It is purely absorption lines. There are packages that can do emission lines. I know, I think SOX is an example of that can do emission lines. Also, if you want to do absorption spectra, SpecWizard isn't the only package available. So there is, for example, Trident is an available package that has links to a lot of cosmological simulations. So that's another thing you could use. So SpecWizard is, that's the thing that I use, which I will therefore, I'm therefore sort of qualified to talk about. These packages do tend to work roughly in the same way. So one thing that they might do differently is you might, they go back to this step. They might go directly from the number of ions, then for each particle, just try to sort of go directly there to a distribution in redshift space, which avoids some issues of possibly binning these things. But on the other hand, one nice thing about SpecWizard is you do have all these, you can get additional outputs that give you, for example, just the ion density along your line of sight without all the peculiar velocity shifts and that sort of thing, which is a useful thing to have in your analysis, for example.
We have a question from Chris. So if I have Z equals 6 QSO, can I use SpecWizard to calculate the stochastic X-ray absorption from the IGM?
Yes.
Great.
That's yeah, as long as you have yeah, I think Eagle data does go out that far. Yeah, that's
okay. Great. So thank you so much again, and we will move on to the next speaker.